Let's consider this recurrence. T of n is 4 times T of n by 2 plus n square divided by log n. If we try to use the master method to solve this recurrence, we need to first lay down what a, b and f of n are. A is 4, b is 2, and f of n is the function n square divided by log n. We then compute what n to the power log base b of a is. That's n to the power log base 2 of 4, which is n square, because 2 to the power 2 is 4. So comparing n to the power log base b of a with f of n, we may hope to land up in one of the three cases of master theorem. So let's try to do a comparison between these two functions. How does n to the power log base b of a compare with f of n? The first thing we can observe is that f of n has a log n term in the denominator, which n to the power log base b of a doesn't. So you can expect f of n therefore to have maybe a slightly smaller rate of growth than n square. And we can verify this by taking the ratio of these two functions. So let's take the ratio of f of n and n to the power log base b of a in the limit as n tends to infinity. F of n is n square divided by log n, and this function is n square. So we get limit of n tending to infinity 1 divided by log n, which is 0. Now, since the ratio of these two functions in the limit is 0, we have confirmed that the function in the numerator f of n has a smaller rate of growth than the function in the denominator, which is n to the power log base b of a. So we can say here that we can say from this that f of n is in big O of n to the power log base b of a. In fact, we could also say something stronger, that f of n is also in little o of n to the power log base b of a. It has a decidedly smaller rate of growth than n to the power log base b of a. But is f of n polynomially smaller than n to the power log base b of a? We note that for f of n to have a rate of growth relative to this function such that we fall into one of the three cases of master theorem, f of n needs to be polynomially smaller or larger than n to the power log base b of a, or it needs to have the same rate of growth as n to the power log base b of a. So we have seen that f of n does not have the same rate of growth as n to the power log base b of a. It is decidedly smaller. So case 2 and case 3 of master theorem are ruled out, because case 2 requires f of n and n to the power log base b of a to have the same rate of growth, and case 3 requires f of n to have a polynomially larger rate of growth. Both those have been ruled out by taking the ratio of these two functions and discovering that ratio to be 0. So what's left is case 1, and case 1 applies when f of n is polynomially smaller than n to the power log base b of a. So to say that f of n is polynomially smaller than n to the power log base b of a means that we should be able to slightly reduce the power of n here by some epsilon and still have f of n being in big O of that function, of the resulting function. So we should be able to chip away a tiny number from the power of n in this function, let's say making it n to the power log base b of a minus epsilon, and still have f of n being in big O of this function. Now, is that true? Does this hold? Well, again, we can check by taking their ratio. So let's take the ratio of f of n to n to the power log base b of a minus epsilon. So without this minus epsilon, the ratio of these two functions was 0. Now let's see what the ratio is if we slightly decrease the power of n here by some small constant epsilon, which is positive. So f of n is n square by log n, and log base b of a is 2. So the ratio becomes limit of n tending to infinity, n square divided by log n in the numerator divided by n to the power 2 minus epsilon in the denominator. So n square and n square cancel out. We can take n to the power minus epsilon in the numerator, and we'll get n to the power epsilon divided by log n. Now this is an infinity by infinity indeterminate form, because the numerator and the denominator both tend to infinity as n tends to infinity. So we can differentiate the numerator and denominator independently by applying L'Hopital's rule. The derivative of the numerator with respect to n will be epsilon times n to the power epsilon minus 1, and the derivative of the denominator is 1 by n. So this becomes epsilon times the limit of n tending to infinity. If we take this n into the numerator and combine it with the power of n here, which is epsilon minus 1, we'll get a plus 1 because of this n. So the result will be epsilon times limit of n tending to infinity n to the power epsilon, which tends to infinity as n tends to infinity. So what we have seen here is that the ratio of f of n to some power of n slightly less than log to the base b of a is actually infinity. When we did not have this minus epsilon, the ratio was 0. So f of n was definitely in big O of this function. But if we slightly decrement the power here, now the ratio becomes infinite. So this means that f of n is not in big O of n to the power log base a minus epsilon for any epsilon greater than 0, for any constant epsilon greater than 0. So f of n is not polynomially smaller than n to the power log base b of a, even though it is smaller than n to the power log base b of a. Right? F of n is smaller than n to the power log base b of a, but not polynomially so. This means that we are not even in case 1 of master theorem. So even case 1 of master theorem does not apply here. This means that none of the three cases apply, because we've already seen that case 2 and case 3 cannot possibly apply, since f of n has a smaller rate of growth than this function. So this is a scenario where none of the three cases of master theorem apply. And that's because f of n falls into this gap along this asymptotic number line, or maybe we should better call it the function line. So it falls into this gap somewhere over here. The red region consists of functions that are polynomially smaller than n to the power log base b of a. The green region consists of functions that are polynomially, the red region consists of functions that are polynomially smaller than this function, and the green region consists of functions that are polynomially larger than this function. And the f of n that we have seen, n square divided by log n, falls into this gap if the values of a and b are such that this function is n square. So if this function is n square by log n falls into this gap over here. It's smaller than n square, but it's not polynomially smaller than n square. What this means is that we cannot use master theorem to solve this recurrence because we are neither in case 1, nor in case 2, nor in case 3. So how do we solve for this recurrence then? Even if we can't exactly solve for it using master theorem, we could still use master theorem to narrow down the range in searching for the asymptotic complexity of T of n. So maybe we can still come up with an upper bound for T of n and a lower bound for T of n and say that, well, the actual asymptotic complexity of T of n will lie somewhere between this lower bound and this upper bound. So how do we get an upper bound for T of n? This function f of n, which is n square by log n, is the amount of work needed to combine the solutions to these subproblems. So let's assume that the amount of work had been n square instead of n square by log n. In that case, we would have obtained this recurrence. Had this function been n square instead of n square by log n, we would have obtained this recurrence. And this function n square is larger than this function n square by log n. So in modifying this recurrence to this recurrence, we are increasing the amount of work needed to combine the solutions to the subproblems. We are increasing the value of f of n. So if we are able to solve this recurrence, which we now can using master theorem, the value or the exact solution we'll get for the asymptotic complexity of T of n will actually be an upper bound on the complexity of this T of n. So note that I'm denoting this as T sub u of n. So this is an upper bound. This is an upper bound on the actual T of n. Why is it an upper bound? Because by increasing the value of f of n here, the sum of the level sums in the recursion tree is going to be larger than what we would have obtained if we had gone with this function. We are going with this function now, which is a larger function. So what does master theorem say about the solution to this recurrence? Well, a is 4, b is 2. So n to the power log base b of a is n to the power log base 2 of 4, which is n square. And f of n is also n square. So f of n and n to the power log base b of a have the same rate of growth, and so we cleanly fall into case 2 of master theorem. This means that the solution to this recurrence is theta of n square times log n. So n square times log n is an upper bound on the asymptotic complexity of this T of n. Likewise, we can obtain a lower bound on the asymptotic complexity of T of n by decreasing f of n to n So if we change this function from n square divided by log n to n, we will be removing this log n from the denominator, but we'll be removing an n from the numerator. So we'll be removing n divided by log n. So the resulting function will definitely be smaller, because even though we removed log n from the denominator, we removed something that was growing even faster than log n from the numerator, which is a power of n. So we can decrease f of n to n and solve for the resulting recurrence. The solution to this recurrence will be a lower bound on t of n, which is why I have represented it as t sub l of n. This will be a lower bound on t of n. So what does Master Theorem say about the solution to this recurrence? Well, a is 4 again, b is 2. So n to the power log base b of a will again be n square. But f of n this time is n. So f of n is polynomially smaller than n to the power log base b of a. So we are in case 1 of Master Theorem. Therefore, the solution to this recurrence, as given by case 1, will be theta of n to the power log base b of a, which is n square. So we can say therefore that the actual asymptotic complexity of t of n will be something larger than n square and something smaller than n square log n. So we can say that the asymptotic rate of growth of the original t of n will lie between these bounds. The upper bound was n square log n, the lower bound was n square. Now it turns out that the actual rate of growth of t of n is n square times log n. You can notice that this function is asymptotically sandwiched between these two functions. It grows larger than n square, but it grows it is smaller than n square log n, because this function has an extra log. It's log n. I won't go into how we actually solve the recurrence to arrive at this actual rate of growth, because the point here is not how to solve the recurrence. The point here is that we can't use Master Theorem to solve such recurrences. But we can use Master Theorem to solve for massaged version of the original recurrence. We can use Master Theorem to help us to narrow down the range of complexity of t of n by giving us an upper bound and a lower bound. So we can choose a convenient function f of n that is larger than this function and get an upper bound on t of n. And we can choose another convenient function that is smaller than this function and get a lower bound on t of n. And thereby we can claim that t of n will have a complexity or a rate of growth lying between these two bounds. This is the distance to which Master Theorem can take us for such recurrences. And we have seen an example here of a function for this given n to the power log base b of a, which falls into this gap. So we have to note here that Master Theorem does not always apply. There are functions that fall into this gap which are not polynomially smaller than n to the power log base b of a, even though they are smaller than n to the power log base b of a. And for recurrences of that form where we have such functions, we can't use master theorem.